Hi, I'm Aidan from the Collins Hill branch of the Gwinnett County Public Library System. This is the second in our series of Codemaking and Codebreaking, a series of videos where we talk about codes and ciphers, how they were created, how they're used, and how you can solve them.
In our first video, we discussed two of the earliest ciphers, @bash and the Caesar shift cipher. They are two of the simplest examples of what is called a monoalphabetic substitution cipher. Now that's quite a mouthful, but what does it mean? A substitution cipher replaces one letter with another letter or symbol. Mono is a prefix for a word meaning one. So monoalphabetic means those changes are always the same. A letter or symbol will have the same meaning at any point in the message or document.
Today we're going to be looking at two different examples of monoalphabetic substitution ciphers. The first one is the mixed alphabet cipher. The other one is the Pigpen cipher. Just like last time, I encourage you to play along at home. From time to time, you will see a pause symbol appear on screen. It's going to look like this. When you see it, hit pause, grab a piece of paper and some pencils, and see if you can crack the code yourself. So, let's get started.
We begin with the mixed alphabet cipher.
So if we think back to the examples we used last time, there were 25 different variations that you could do. If we look at the mixed alphabet cipher, if we imagine that we're mixing up all 26 letters and putting them in any different combination, instead of having 25 different options, we have over 403 septillion combinations that we have to pick from. Now, while a lot of those will leave the alphabet in enough of an order that they're unhelpful, there are certainly plenty more options to pick from, making these at least a little more secure from brute force attack.
You start by writing the alphabet from A to Z. Then pick a code word and write it in the spaces underneath. If a letter in that code word has already been used, you skip over it and move on to the next letter. When you complete that code word or code phrase, you write out the remainder of the alphabet in order, taking care to avoid repeated letters.
The great thing about this cipher is that the shifts are not uniform. Let's say I've worked out that H represents the letter D. It doesn't help me understand what any of the other letters in the alphabet are. We still have to go through that same process of trial and error to find each individual letter.
We do have to take care though. In this example, I used the code word tigers. That is a short and memorable word, which is good. It will be easy for the person receiving that message to remember. The problem is that if you look, you can see that the last 6 letters of the alphabet represent themselves. The solution to this is to make sure your code word or code phrase uses at least 1 or 2 letters from late in the alphabet. I have changed from tigers to zebras, and you will see that fixes the problem. Remember that the longer your code word or code phrase, the more random your order will appear.
Okay, so let's go and try and solve one of these together. Now, imagine that you've received this coded message. You'll have been told in advance that the keyword is zebras.
We will write out our grid and start shifting the letters. Remember that the message we have received will take letters from this arrangement with the code word and the translation of the letter immediately above it. For example, R will be D. At this point, pause the video and see if you can work out the rest of the message yourself. Did you manage it? Well, hopefully you did.
So, as we talked about, it's very hard to beat a mixed alphabet cipher through simple guesswork. Fortunately, the person who's trying to defeat it has another tool they can rely on. We're going to be talking about it later in this video. It's called frequency analysis. But first, let's talk about our other code, Pigpen.
Here is an example of a code written in Pigpen. Now, this is one of the most famous ciphers, in part because of its very distinctive look.
Now, at first glance, it doesn't look like letters at all. Instead, it's a series of symbols. Where do those symbols come from?
The symbols come from a set of grids that are used. 2 tic-tac-toe grids, one of them having a dot in the corner of each box, and 2 X grids, one of them also having a dot in the center. The person filling in the grid usually works from left to right. To use a letter, you simply draw the lines in the dot, if any, that appear around it on the grid. This, for example, represents our letter M. Let's take another look at our sample message. Now is a great time to pause and see if you can work out the letters for yourself. Now, I added a little trick here. I removed the gaps between the words. The message is, this is an example. Was it easy?
The problem with Pigpen is it is simply too well known. Its system of symbols is instantly recognizable. So it typically gets used today in games, books, and puzzles. Now, Pigpen is also susceptible to that system of frequency analysis. So let's begin by talking about exactly what that is.
Frequency analysis was discovered by the mathematician and cryptographer Al-Kindi.
Now, what Al-Kindi realized is that even if you don't know another language yourself, you can notice things about it, because languages have personalities.
We know, for example, there are only a small number of 1 or 2 letter words in the English language. We also know that only a few pairs of letters appear alongside each other, like SS or TT. Using the techniques Al-Kindi describes, we know exactly how common each letter is in the English language. We can compare the percentage of times a letter or symbol appears in a message with its usual frequency. The longer the message, the more accurate this technique will be.
So frequency analysis is most effective when you have passages and passages of text. So those are the basic steps in how to perform frequency analysis. It is a complicated process and it can be time consuming. But the thing that is so impressive is that you're able to decode messages even if you can't speak the language that you're decoding them in. As long as you have enough of a sample text of undecoded language and enough of a sample of the coded. One of the most important tools at your disposal will be your dictionary. You'll be able to use that to see if it's possible that there could be a word that looks like the word you've decoded. If you know that it's wrong, then you know that something has gone wrong in your frequency analysis and that you need to go a step or two back and try again.
Now here we have a message. I've gone ahead and counted how often those letters appear. I then worked out the percentage of times that letter is used. The most common letter in the English language is E. Now, the most common letter in this encoded passage is C. If we look at the percentages, they are almost exactly the same. Now, we can try substituting E for C in the passage and see how it appears. I'm going to color code the changes I make so you can see what I've done. Now, if you're doing this at home, it's better to write your message out with some spacing above and below each line, and then make your notes in that gap. The next most common letter is T. Z appears a little bit more than is typical, but that reflects that this is a short passage. The longer the sample, the more likely it is that these percentages will be accurate. The next few percentages are quite close together. Now, we could experiment with trial and error, but let's think back to a few of the tricks we talked about in our previous session. In particular, think about 2 and 3 letter words. I've highlighted one of these, TRE, which appears twice. We have decoded the letters on either end of the word. How many 3-letter words in English begin with T and end in E? There are 6. Tay, tea, the, tie, toe, and chew. Now, T isn't possible because we've already found which letter represents the letter E. So it must be one of the other 5. The most common of these is the. So let's see what happens if we replace the letter R with H throughout the document. So looking at this, the letter doesn't look wrong anywhere else. What's more, it gives us another word that looks almost complete. If we use the same trick, how many different 4-letter words begin TH and end in a T? Let's assume that the highlighted word is that. The letter A is the 3rd most commonly used in the English language, and the letter I is the 4th most used in this document. Now, that's not exactly the same, but it's close enough that it is a reasonable guess, so let's go with that. Nothing appears to be obviously wrong. Now, let's take another look at our frequency charts. O is the next most frequent letter, and W is the next most frequently used in the passage. What happens if we try plugging that in here? So here things don't look right, and we have a few words that really indicate this. There are only 5 words in the English language that begin T-H-O. And of those, the only one that is common is thou. Now, unless we know this is a very old text, it is unlikely that thou would feature frequently, if at all. And O is extremely uncommon as a one-letter word. Really, you only find that in poetry. A much more common one-letter word would be I, and that would also make sense of our 4-letter word. If we look at our frequency chart, that is the next most likely letter to be used, so let's try replacing it with that and see what happens. This looks much better. We can see that in a short passage like this, the frequency analysis chart will not always map up perfectly to the code used. We still need to use our human interpretation and some of those tricks that we learned to make our work easier. Now let's use that trick one more time. If we look in the dictionary, there are only a small number of 4-letter words that begin T-H-I, and the only common ones are this or thin. But let's apply the context of the passage. Do sentences or clauses commonly begin with thin? It is much more likely that this will be used, particularly given it features 3 times in the document. Let's assume that U represents the letter S and see what happens. So this is looking pretty good, isn't it? Now this process is not fast, but if you take your time and work methodically, you can soon begin to whittle down your options to something manageable. Now, at this point, if you want to try this for yourself, pause the video, copy down the message, and test out some options. Now, remember that every coloured letter here has been correctly placed. Look at the frequency charts and see what happens if you switch out some letters. Make sure you use pencil though, because you'll probably need to make some changes. And remember that it is better to leave some space above the words so that you can work out what you need to switch than altering the passage itself. So let me show you how I would solve this. 2-letter words starting with an A could be an, as, or at. Now we've already used S and T, so the highlighted word must be an. Looking at the dictionary, the only options for the highlighted word are anabasis, which is impossible because we've already mapped A, or analysis. In this cipher, L and Y actually represent themselves, so let's apply that to the rest of the passage. Did you notice that there's a 2-letter word beginning with T? That suggests it might be the word to. This is the most common remaining letter in the text, so let's try substituting O in place of A, and we'll see what happens. Filling in that letter makes some other words really leap out at us. Clearly the P will be replaced with an R to make another and other. Yo should be you, so E represents you. Let's do that and see what we get. This word looks like substitution. At this point we can read almost all of the text. These words look like using and interesting. This phrase looks like will be substituted for. Let's plug those in next. The next most common letters remaining are S in the passage and C in the alphabet. Now, if we look at this highlighted word, it makes sense. The next most common letters after that are Q in the document and M in terms of English usage. Substituting that makes sense of the highlighted word, giving us mathematical. Look, we're almost there. At this point, you can probably read the rest of the text. Knowing the likely subject of the text helps with translating it. We could recognize enough words to know that we are looking at a document about code breaking, and that suggests some likely translations. This word would be cipher. This word must be equations, so K represents Q. This looks like example. We have just 2 letters left now. These can be solved by plugging in the 2 most likely letters. V replaces J and K replaces G.
So, that's how you perform frequency analysis. Now that you've learned the basic idea behind it, how about you put those skills to the test? Sherlock Holmes decodes a series of coded messages in the short story The Adventure of the Dancing Men, and you can see the characters that he's decoding in the text. Another opportunity to use those skills is in Ian Colfer's series, Artemis Fowl. At the bottom of each page, there are a series of different codes, 3 in total. Can you use your frequency analysis skills to defeat them? Thank you for joining me for this session of Codemaking and Codebreaking. I hope that you'll join me next time when we'll be talking about transposition ciphers. Thank you.